Okay, we are recording and we're here in week 5. So let's see. Today, y'all, is September the 21st. So today, guys, what we're going to do, we're going to go over 3.4. Once I'm done with 3.4, I am going to upload the video by this afternoon, y'all. Usually it's uploaded, before 2 o'clock, but I'm definitely by 5, okay? Guys, remember, homework for 3.4 is not due until a week from tonight on the 28th. All righty, so let's see. Week 5, we're going to start with, let me scroll back up here to the very, very, very top where we are with 3.4, okay? Let me just make sure that my mic is working for the recording. And okay, we're good. Okay, so guys, for 3.4, we're going to talk about multiplication of whole numbers. So it says in the grade 3 Common Core standards, we find that students should be able to interpret the product of whole numbers, interpret 5 times 7 as the total number of objects in 5 groups of 7 objects each. For example, describe a context in which a total number of objects can be expressed as 5 times 7. Okay, so the idea here, y'all, is, remember, multiplication is the idea of repeated addition. We're adding the same number over and over and over again, okay? So what we're saying is right here, if we have n times a, what that means is we're adding up the number a n times, right? However many times that happens to be. So it also says that the repeated addition model can be illustrated in several ways. For example, using colored rods of length 4, the combined length of 5 rods can be found by joining the rods end to end. So if you notice here, we have rods of length 4, and we have a total of 5 of them, and that's why the total adds up to 20, right? If you notice, y'all, what they did right here is they said, look, let's cut that little rod in half. So we cut that little rod in half. We have 4 and 4, which is 8, and half of 4, which is 2, that gives me that 10 and that 10. So we can say, look, we have 2 rods, bigger rods of length 10. When we add those together, that's 20, okay? Now, there's also the idea of using the number line. So if we're doing 5 times 4, we're going on the number line. We're going to go 4 spots and another 4 spots and another 4 spots, and we're going to do that 5 times. And where do we end up with? We end up with 20, okay? We also have something called rectangular array and area models, okay? So again, I don't know about you guys, but I remember elementary school for me was a pretty great experience. I really liked elementary school. Junior high, not so much, right? Junior high is kind of a hard age, 13, 12, 14. But I remember I really enjoyed elementary school. And even though I struggled with math as a kid, the idea of using like pictures for me to understand multiplication always came in really helpful. So what I want to do is I want y'all to look at this picture of donuts over here that we have on the right side. And I'm going to take a little screenshot of just this piece right here, okay? So let me take that right there. Let me copy this guy over. And y'all, what I want to do is I want to paste it right here. But what I'm going to do is, let me click on this. I'm going to rotate it. There we go. So as a kid in elementary school, and I don't remember what grade I was in, but I remember that when I looked at this kind of a picture, and my teacher, I think it was her name was Mrs. Gano, was showing me how to do this. She was like, look, let's see how many donuts we have, right? And she would say, look, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So it said, okay, look, we have a total of 12 donuts. And she would tell me, Omar, listen, we're going to think about these things here as rows, and we're going to think about these going down as columns. So she's like, look, we have 1, 2, 3 rows, right? And we have 1, 2, 3, 4 columns, right? So she would say, look, now I want you to notice something. If we rotate the picture, we didn't change how many donuts we have there. We still have a total of 12 donuts, but now don't we have 1, 2, 3, 4 rows? And now don't we have 1, 2, 3 columns? And the idea of looking at that picture, whether it's sort of long ways like this or up ways like that, helped me understand one of the really important ideas in math is that when you multiply two numbers, it doesn't matter what number you multiply first and what number you multiply second. So if I were to think of this one here as, say, 4 times 3, and I were to think of this one here as 3 times 4, I know I'm still going to end up with 12. And as a young kid, in like fourth grade, so I don't know, I was maybe like 10, I remember that experience helped me understand multiplication a whole lot better. And just looking at the picture and just the fact that she just rotated it made it much easier for me to understand and gave me the idea of what multiplication really means. So I wanted to go through that there because, again, that's an important part of teaching younger students on how to do multiplication and what it really means, okay? So let's see. Another thing we have now are these kind of sticks, and we call them like array points. And what we're looking for is the number of intersection points, okay? And so when we look at these things here, we can figure out, okay, how many little dots do we have? How many times do those lines intersect? And I kind of hate looking at this now that I'm a little bit older because it's always kind of bugs my eyes a little bit. But I can see I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it looks like we're probably going to have, what, 20 little dots as we go through. So there's 20 right here. And then they also show me the picture of doing like a grid, okay? So how many little squares do I have? And so, y'all, this is something that you may be somewhat familiar with, maybe you're not, but at any point in time, if you decide, what, I don't really like the floor in my kitchen, and I want to redo the floor in my kitchen, or I want to put new carpet in my bedroom, or I don't want carpet in my bedroom, and you're going to redo the flooring in there. Anytime we redo flooring, we measure flooring, y'all, in something we call square feet or square yards and things like that. So if we were to look out in the hallway, and actually this is not a really good example of a hallway, but a lot of times when we have a hallway, or even think about like when you were in school, the floor had those little square tiles, right? And the reason why they're square tiles is if we were to say, look, if I have an area, say just a little part at my house, here we go, that's 4 by 5 feet, what we're really doing is we're saying, how many tiles do I need? Well, I need a total of 20 tiles, and those tiles are in square feet because each one of them is 1 foot by 1 foot, and that's what we call square feet. But again, that's kind of a different idea, but just the idea of how many tiles do I need? I need 20 of them, okay, because I have a 4 by 5 foot sort of area, okay? Alrighty, so the next part I have here, you guys, is something called the Cartesian product, okay? And it says, excuse me, the Cartesian product of set A and set B symbolized, and look how they write it. It looks like A times B, right? But the way I really read that is A cross B, okay? Is the set of all possible ordered pairs in the form little a, little b, where little a is part of the set A and little b is part of the set B. So I want to explain what I'm going to do here. Here is my first two sets, A and B. And we're looking for what we call the cross product of A and B. So this here, y'all, is going to be a set. So this is kind of how we write, come on, pen. This is kind of how we write our sets, okay, with those kind of little squigglies. Now, what we're writing here, you guys, are pairs, okay? We're going to make every possible pair where the first number or the first spot is going to be something in A and the second spot is going to be something in B. What I mean by that is I'm going to go, look, let's go 1 in A, and then let's go 1 in B. And then we're going to go 2 in A, and we're going to go 2 in B. And we're going to do this 2 more times. We're going to go 3 in A, and I'm kind of running out of room here, so I kind of had to shove that guy in there, and 3 in B. And we made every possible pair that we can make where the first spot is a number in A, and the second spot is a letter in B. So A and A cross B, always the first spots have to be parts of the set A, and the second spots always have to be elements in the set B, okay? Now, The second question says, hey, does A cross B, is that the same thing as B cross A? I don't know. I know what A cross B looks like. Let's see if we can find B cross A. Okay, so I'm going to start making sets. Now, y'all, when I make my sets, the first spots are going to be letters in B. So look, I'm going to go A1 and A2 and A3, and then I'm going to do the same thing for the next part. B1, B2, and B3, okay? Now, the question now is we want to know, does this set here, is that the same thing as this part right here? Are they in the order? No, they're not, right? Because we have 1A where we have A1. So the order really is important. So when the question says, does A cross B equal to B cross A? What I would say here, you guys, is we'd say no, it's not, okay? All right. Now, the third part to the question says, determine N of B cross A. So remember, when it's asking me to find N of B cross A, what they're asking me for is how many elements are in this set. Now, the elements, y'all, are each of the ordered pairs. So I'm just going to count how many ordered pairs we have. And it looks like we have 6 ordered pairs, right? All right, so I'm going to kind of keep scrolling along here. And let's take a look at this next problem. And it says, show that 8 times 3 equals 24 using each of the models in parts A through D below. Okay, so we know that 8 times 3 does give us 24, okay? So y'all, the first thing we're going to do here when we look at the first part is we're going to use the repeated addition number line. Now, one thing I want you to notice about this problem here is that they all end in what number? 24, right? Which is what we have right here. So that's not really the point. The point is which one of those number lines shows us either adding up the number 3 8 times or shows us adding up the number 8 3 times. Well, wouldn't you guys say D does, right? Because it has the number 3 8 times, right? So look, 124, yeah, that's still 24. 4 6s, yeah, that's still 24. 6 4s, yeah, that's still 24, but that's not what it's asking me. It's asking me which is the one that shows the 8 times 3, okay? Now again, y'all, we're still dealing with 8 times 3 equals 24. So we have the rectangular array model. Now remember, the rectangular array model, again, I'm looking for the same thing. Which one has 24 little dots? Now they all have probably 24 little dots, but which is the one that has either 8 rows and 3 columns or 3 rows and 8 columns? Which one would you say looks more like that? A, B, C, or D? A, right? Because here's my 1, 2, 3. And again, I can count them, but I'm pretty confident right there that there's got to be 8. Okay. All right. Same thing for the grid model, y'all. So again, we're still going with 8 times 3 equals 24. So again, I want to know, I know all of those little grids up there all probably have 24 little squares, but the one that has the 8 by 3 would be grid A, right? That would be the one that has 8 by 3, okay? So again, I'm just using these different models to figure out which is the one that shows the 8 times 3 equals 24, okay? Now, guys, if you notice up here on my notes, I have grid A, grid B, and then I go to grid D and grid C. That's how they do it in my lab. For whatever reason, they just kind of throw them around random there, okay? So just as you're going through it, you're really just looking for which is the one that kind of matches up. It doesn't really matter what letter it is or the order they put them in. Okay, now there is a part D. So again, I want you to notice something here, y'all. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8 right there. 1, 2, 3. Okay, so I still have 8 pieces here and 3 pieces here. I'm looking for the one that's going to have 24 ordered pairs. Okay, so I don't think I have to stare too long But could you tell me which one of those, A, B, C, and D, looks like it has 24 little pairs? D, it has to be D, right? That's one that has 24 little pairs. And again, y'all, I know that just from common sense, right? I can see it's got the most, and it looks like it's got a whole bunch of them there. But again, just to give you an example, the way I find the cross product is I'm going to say, look, make a set. I'm going to make pairs. I'm going to go A with X. I'm going to go A with Y. I'm going to go A with Z. And then I'm going to do the same thing for B. B with X, B with Y, B with Z. And if you notice, hey, look, they're all right there, right? So again, I can visualize this just by looking at the first couple. Okay. All righty. So let's continue here with cross products a little bit, y'all. And the next part here says, if my set A is the letters F and Q, and my set B are the letters T, V, and Z, then the first thing we want to do for part A, we'd like to find the cross product, okay? So if we're going to find the cross product, we're going to make ordered pairs. So we're going to say, look, F and T, F and V, F and Z. And we're not done yet. We're going to do the same thing with Q. Q and T, Q and V, Q and Z, right? So there's my cross product, okay? Now, part B says, how many elements do we have in that cross product? Now, remember, y'all, the elements is how many pairs do we have? So everybody agree we have a total of 6 pairs? Okay, and then finally, y'all, part C. Part C says, write a multiplication equation involving numerals related to the answers in parts A and B. Okay, so we want to see how could we know that we're going to have 6 pairs just based on how many elements A has and how many elements B has. How many elements are in the set A? 2, right? And how many elements are in the set B? 3, right? And isn't 2 times 3 going to give me 6? Because again, we're making all these possible combinations, right? So we got 2 choices in the first spot, and we got 3 choices in the second spot. Then we're going to have a total of 6 choices, okay? All right, excellent. Really good. Okay, so for the next problem that I have here, it says, for each of the following, find, if possible, a whole number that makes the equation true. Okay, so part A says 3 times some number Z is equal to 21. I don't know if I did this or not. And I think I said I was going to do it, and I don't know that I did. Yes, here we go, guys. The first thing I'm going to do, I'm going back here to my Blackboard page. I got a multiplication table right here, okay? I'm going to pull this up because I'm going to use this, okay? So let me come back to my notes. 3 times some number equals 21. So I want to say probably about 3rd grade is probably when we start looking at multiplication tables. And I know we usually look at it maybe a 10 by 10 or a 12 by 12. But I'm going to come back and look at my multiplication table. And I want to figure out when is 3 times something is going to give me 21. And again, I know that we know what the answer is. But what we want to do is you want to be able to show this to kids, right? So if you were showing this to students, right, to younger students, right, elementary school age, what we would do is we'd say, look, let's look at the 3's. And I want to count. Do I see a 21 anywhere? Oh, yeah. How many times do we have to multiply 3 by to get 21? And again, the idea here, y'all, is if we're using our table, what we would say is we got to multiply 3 by what number? By 7, right? That's how you would teach younger kids on how to use your multiplication table. You'd say, look, 3 times 7 is going to give me 21. So right there, I would say, okay, well, Z's got to be equal to 7. Okay. Now, part B. Part B says 36 equals 18 plus 3 times Z. Okay. So the first thing we would probably say is, look, we're going to multiply 3 times some number. And then whenever we get our answer here, we're going to add 18 to it, and we're going to end up with 36. So if I want to figure out what do I have to multiply by so that I add 18 to it and I get 36, we might first say, well, look, let's get rid of this 18 first, okay, by subtracting it on both sides, okay? And again, you would show your students how you want to subtract, right? If you want to do, some kind of an adjustment, right? But we know that 36 minus 18 is going to be equal to 18, okay? So now we have 3 times z equals 18. Again, if I was showing this to younger students, I would come back to my multiplication table, and I would come back to my 3, and I would scroll down until I find 18, and I would say, okay, well, look, I have to multiply 3 by 6 to get 18, right? And again, I know that this is stuff that I'm not telling you anything new. I'm not telling you anything that you didn't already know. What I'm trying to show you is that this is how you would do this. This would be the approach if you're going to show second graders or third graders or fifth graders or whatever it happens to be, right? And obviously, if you're dealing with, somebody younger, maybe you're not even going to go that far. But z is going to be equal to 6, right? Okay, now for part C, and I'm going to admit right now, y'all, part C is a little bit more of an advanced problem. I don't necessarily know that you're going to show this to elementary school kids. Again, I don't have any experience teaching that age group. Did I do this when I was in 4th grade? I don't know. But I'm going to show you the idea here. Okay. Z equals 7 plus 6 is equal to z times 7 plus z times 6. Okay. Okay. So what you might want to do is you might say, look, let's try it this way. 7 plus 6. I know 7 plus 6 is, say, 13. Okay. So I'm going to make this up. Let me pick a number for z. I don't want to pick the number 1, you guys, because 1's kind of a boring number. But suppose I pick z equals 2. Okay. What I want to do, I want to check something here. If I were to multiply 2 times 13, so again, I would go back to my chart, and I know that 2 times 13 is going to give me 26. Okay. What I would want to check is if I multiply 2 times 7, and I multiply 2 times 6, and if I add those numbers together, would I still get 26, right? So then I would go back to my chart, right? And again, this is just how I would approach it with kids, right? And I'd say, look, 2 times 7 is going to give me 14, right? So I'd come back over here. And again, I know you know that that's 14. And you would do the same thing here, and you'd say, look, that's 12. And we'd add those together, and we'd say, hey, look, we're going to get 26, right? And then I might say, look, you know what? Let me try that again. And I would pick another number like 5, and I would go through that same process, right? And to give you an answer, yes, it's going to work, right? It's always going to work, right? So then when I'm doing this part for part C, I'm going to say, you know what? This thing is going to work for all whole numbers, right? But again, if I was sitting in a classroom full of a bunch of, 4th graders, that would be my approach and how I would do something like that. That's how I would show them, because then it's visual. We can check, hey, look, is it working? Yeah, look, it worked for 2. Okay, let's see if it works for 5. Yeah, it worked for 5. And with younger kids, you might need to do it another time. You might say, look, let's try 8. And we would try 8. And we would say, hey, look, this seems to be always working. Does it look like it's always going to work? Yeah, it looks like it is, right? And then you would kind of do that model. All right. So let's take a look here at the next problem. And it says a designer has designed different tops, pants, jackets, and to create outfits. How many different outfits can the models wear if she has designed the following pieces? Okay, so we have 2 tops, we have 4 pants, and we have 8 jackets. And we want to figure out how many different outfits can we make. Y'all, all we're going to do here is multiply, because we're going to create, kind of like the way we did that cross product, we're going to create every possible, in this case, we wouldn't have ordered pairs, we'd have triplets, right? 1 top, 1 pant, 1 jacket, and then the second top, so on and so forth. So if I were to multiply this whole thing out, I want to say I'm going to get something like 64. Now, y'all, when I was making my notes, again, you can see for the most part, I take these problems directly from your homework. But I want to look at this next problem here, and it says a new model of car is available in 4 exterior colors and 5 interior colors. It says use a tree diagram and specific colors to show how many color schemes are possible for the car. Okay, so let's think about this for a minute, and then we're going to go to MyLab just to kind of verify some stuff here. So look, we have 4 exterior colors, and we have 5 interior colors, right? So if we wanted to know how many possible color coordinations, do you guys agree we're just going to multiply those two numbers out, right? And so we know we're going to end up with a total of 20 different possible combinations. Now, the directions here tell me real specifically, they say, look, use a tree diagram and specific colors to show how many color schemes are possible for the car. So what I want to do here, you guys, is I'm going to do like a tree diagram. So what I mean by a tree diagram, it's going to look something like this, okay? And so I'm going to pick my exterior colors here. So I don't know, I'm going to go red, black, silver, and gold. Okay, I'm just making up 4 colors. Now I need to come up with 5 colors for the inside. So look, let me go like this. 1, 2, 3, 4, and 5 right there. So let me pick 5 colors for the inside. Oh, I don't know. Let's go with tan, black, gray. That's going to be too many B's because then I'll confuse them. I don't know about you guys. I don't want a red interior car, but some people do. Red. And anybody got another color you want to throw out there? Yellow for the inside of your car. Okay, cool. Yellows. So, okay, so now let's take a look, y'all. Remember what this means. The outside of my car is red. So I could have an outside car with red, inside with tan, red and black, red and gray, red and red, or red and yellow, right? And then we would do the same thing here. Like I would make those same 1, 2, 3, 4, 5, right? With still tan, black, gray, red, and yellow. And then I would say, look, we can have a black car with tan interior, or black outside and black inside, or black outside and gray inside, and so on and so on and so forth, right? So again, I just kind of made this up. But what I want to show you guys is, let me come back over here. Okay, so let me go to my page right here, guys. Look, I'm going to go to MyLab because I want to show you how that particular problem looks in MyLab. Okay, so look, I'm going to click on assignments right here. All right. And so 3.4 is already open, right? I got a ton of questions here. I don't know. I don't know which one it is. I'm going to look for it right now. Okay. It's which one? 5? Here we go. Okay, so it says use a tree diagram. So look, we have 3 exterior and 2 interior. So I know I'm going to have a total of not 5, but 6 because we're multiplying. There we go. Okay, it didn't even ask me to do a tree diagram. Sorry. Okay, it said use the tree diagram, so I drew the tree diagram, but it didn't really even ask me to do that. Okay, I wasn't sure how it was asking me to answer it, but straightforward kind of stuff, right? But again, I think the idea here, you guys, is even though I went through all that process and didn't really need to, you're kind of showing why it works the way it works, okay? Okay, so y'all, we have some properties of multiplying whole numbers. The first one is called the closure property, and we talked about the closure property of addition. So remember what the closure property says. If you got a set of numbers, and now we're dealing with multiplying, I'm going to multiply every possible combination of those numbers that I have, and if I end up with a number that's still in my set, then we're closed. And if I end up with a number that's not in my set, then we're not closed, okay? There's something called the commutative property. The commutative property, y'all, is what we were talking about earlier today when I did this thing right here with the donuts. In that, which number I put first and what number I put second, it doesn't make any difference, because if you notice, look at the picture, I didn't change it all. I still got 12 donuts, right? That's what the commutative property says. Which one you do first, which one you do second is not really important, okay? So let me scroll back down to where we was. Okay, here we go. The associative property. Y'all, the associative property refers to when we are multiplying more than two numbers. So 3 numbers or more. I want to explain that by this problem that we did over here. When we did the 4 tops, or the 2 tops, I'm sorry, the 4 pants and the 8 jackets, I know I didn't really write anything out here, but the way I really did this multiplication in my head was I said, come on, pen. I said, look, what's 2 times 4? What's 2 times 4? But you're multiplying. 8. What's 8 times 8? 64, right? So I really did the first 2 first. Now, the associative property says, you know what? And I did it that way, you guys, because I know 2 times 4 is 8. But everybody thinks a little bit differently. If I would have said, look, let me multiply those 2 numbers first. Anybody know what 4 times 8 is? 32. What's 2 times 32? Still 64, right? Everybody's mind works a little bit differently. For some people, like for me, it was much easier for me to say 2 times 4 is 8. And I know 8 times 8 is 64 because they drilled that into my head ever since I was in 3rd grade, right? But as we got a little bit more advanced in math, we started doing things like 4 times 8. And for some people, they look at 4 times 8, they say 32, now double that, there's your 64. That's what the associative property says. Which one do you do first? Which one do you do second? Makes no difference. Okay, then we have something called the identity property of multiplication. The identity property of multiplication, y'all, just says, when you multiply any number by 1, you still get the same number, right? So we know 4 times 1 is 4, 8 times 1 is 8, that kind of stuff. Okay, so now let's talk about whether the following sets are closed under multiplication. Okay, in order for this to be closed under multiplication, you guys, what I need to do here is I need to take every possible combination. Well, 0 times 0, that's still in my set, it's right there. 0 times 20, still 0, that's still in my set. Now, I don't really have to do 20 times 0, y'all, because of the commutative property. But what I need to know is, what's 20 times 20? Anybody know what 20 times 20 is? 400, right? Is that number in my set? No, it isn't, right? So for part A, oh, come on, pen. It's not closed, right? It's not closed because when I take 20 times 20, I get 400. That's not in that set of numbers there, okay? Let's do the same thing for part B. Okay, let's look at part B. Now, you guys, look at that set in part B. 10, 20, 30. The little dot, dot, dots means it goes on forever, doesn't it? Okay, so look, let me ask you a question. If I were to take 10 times 10, I would get 100. The question I want to ask you, do you think 100 would appear somewhere further down that line? Yeah, it looks like it would, wouldn't it? Okay, let's try something different. Let's try, say, 20 times 30. That would give me 600. Do you feel like 600 would also be somewhere down that line if I kept going? Right? Okay, now guys, let's try something a little bit harder. Let's try 100 times 600, because we know those are numbers that are going to be in our set. So we took 100 times 600. 6 times 1 is 6, and then I got 2 zeros and another 2 zeros, so 1, 2, 3, 4 zeros, 60,000. I might have to go really, really far, but wouldn't it be in that set as well? Okay, so now what we can say is, yes, it's closed, right? Because for every different pair we come up with, yeah, it's still going to be in there, right? Okay, now let's look at the set C. So here's my set C. I'm going to do the same thing here, y'all. I'm going to go 10, 12, 14, 16. And again, we're going to go on and on forever. So y'all, if I look at the set C, Does everybody agree that the set C, they're all even numbers, but they're even numbers that are bigger than or equal to 10? Because it's 10, 12, 14, 16, so on and so forth. So let's play that same game. If we were to take 10 times 12, that would be 120. Now I know 120 would be in there because it's still an even number, right? Now we could say, look, let's try something big here. Let's try 16 times 120. Okay. Now guys, forgive me, but I'm going to use my calculator for this. 1920. Okay. Wouldn't that number also still be in my set because it's still an even number? It's still bigger than 10. So I'm going to say, yes, it's closed. Okay. All righty. So let's keep moving along here. And guys, I think I made a little mistake. Here we go. Not a huge mistake, but a small mistake in that here is my distributive property. There's the distributive property. And again, we probably learned this in algebra at some point in time. But the distributive property of multiplication over addition just says, if you're multiplying a number A times this quantity, B plus C, you can multiply those and then add them together. Okay. So the reason why I wanted to go over that first is because the two previous problems say, let's use the distributive property. So I really should have moved this up a little bit higher. Okay. So apologies. All right. So let's go ahead and take a look at what it is we have. Okay. So we're going to rename each of the following using the distributive property of multiplication over addition so that there's no parentheses. Okay. So guys, if you remember this, you probably remember this a little bit maybe from high school or maybe even from college algebra, but there's something called the FOIL method, right? And you might say, look, you know, if I'm going to teach third grade, why am I going to teach the FOIL method? You're probably not. But class gives you the, once you go through the education program, you can really teach anything from K to 8th. And in 7th and 8th grade, they're probably going to see some of this stuff, okay? So anywho, the FOIL method. I don't know if you remember this or not, but the F stood for let's multiply the first pieces together. So we're going to multiply those guys together. So A times C, I'm just going to put an AC, okay? And then the O stood for the outer ones. Now the outer ones are these over here. So A times D is going to give me an AD, okay? And then the I stood for the inner terms. So we're going to multiply those together. So B times C is going to give me a BC. And then the L stood for the last terms. So the last terms are these over here, and that's a BD, okay? So again, just so that you know, and I'm going to write it over here on the side, what the FOIL method stands for: the first, the outer, it's supposed to be an E, the inner, and then the last, okay? And that's something we call the FOIL method. Again, they show that to students probably in like 7th and 8th grade. So again, remember, like I said, when you get your education degree, you can really teach anything between kinder and 8th, and where some people may really have more of a desire to teach 2nd grade or 3rd grade or 4th grade. Some people do have a desire to teach 8th graders, right? That might be something they want to do. I think that's a hard group to deal with. I don't know about you guys, but junior high seems to me like it would be. Anybody want to do junior high here? No? No? You shook your head like, not just no, but like hell no. Yeah, I know. It seems like it would be a rough group. Okay, y'all, let's do the same thing for part B. I substituted, when I was in college. I worked as a substitute teacher, and my dad was a junior high counselor in Ed Couch Elsa. And this was a long time ago. This was like in the, I don't know, mid to late 90s. And I worked as a substitute for junior high, and it was quite an experience. It was a little rough at times. Other times it was really great. All right, so again, I'm going to use the distributive property. I'm just going to multiply this x times each of those pieces. So that's going to give me an xt plus an xo. And again, all I'm trying to do here, y'all, is I'm trying to remove my parentheses, okay? Now we got a third part right here, part C. Part C says we have A and then B plus C minus an AC, okay? So again, I'm going to do the same thing here. I'm just going to distribute my A. I'm going to multiply the A to both those pieces. So that's an AB plus an AC, but I want you to notice something. I'm also subtracting an AC. So since this piece right here and that piece right there are exactly the same, but one of them is being added and one of them is being subtracted, those pieces, y'all, are just going to drop out and we're going to end up with our AB, okay? And the reason they're going to drop out is they're both the same value, but one of them is plus and one of them is minus. And again, you know, if those of you who do teach junior high, and I know those of us who are sitting here don't really have a desire to teach junior high, but when you teach junior high and you start talking about subtraction or you start talking about negative numbers, I know we're dealing with whole numbers here right now, but I always tell my students, and I do this in all my classes, but think of a positive number as how much money you have, and a negative number is how much money you owe. So just for instance, if I said that was 5 and that was minus 5. So if I had $5 and I owe you $5 and I pay you, we're even Stevens, right? Okay. So for the next part, it says use the distributive property or using the distributive property of multiplication over addition, we can do something called factoring. So again, this is probably stuff that more junior high students would see, okay? What we're really doing here, y'all, we're going backwards when we're factoring, okay? So look at part A, and it's xy plus y squared, okay? So just so that I have an understanding of what this really means, what this really means is that I have xy plus y with another y. Y squared means that there's two of them, okay? So what I'm going to do here is I'm going to look at this piece, I'm going to look at that piece. And if I look at this square and I look at that square, do you agree with me that they both have at least one y? So what we can do here, y'all, is we can take that y away. Now, if I take the y away from here, I'm left with an x. And if I take one of those y's away, I'm still left with another y. And what do we have in the middle? We had a plus, so we keep it with a plus, okay? And if I wanted to check my answer, I could say, look, y times x, same thing as xy, and y times y, same thing as y squared, okay? So look, let's do the same thing for part B. So I'm going to write xy plus x, okay? I'm doing part B on the side, y'all, because I'm kind of running out of room. Okay, so I'm going to play the same game that I played before. I'm going to put this in a box, and I'm going to put this in a box. And I can say, look, you know what I both have? They both have an x. Now, y'all, just in case you didn't know, or in case you forgot, the number in front of that x, yeah, it's really a 1. So if I take that x away, I'm still left with a y and a plus 1, okay? A lot of times people will ask me, sir, do I really need to put the plus 1? I do, okay? Because if I didn't put the plus 1, I would just have an xy, and I wouldn't have that other x over there. Okay, and let's look at part C. A squared b plus ab squared. Okay. A squared b plus ab squared. Again, y'all, the way I would do this problem, again, if I'm teaching, say, 7th graders or something like that, or 8th graders, this is probably how I would write it out. And I would look at this box here, and I would look at this box here, and I would say, look, that A and say that A match out, so I can take an A, and this B and one of those B's can take out, so I can take out a B. So if I took away this A and I took away this B, what am I left with? Still left with an A. Now I have a plus in there, so I'm going to put a plus in there. And if I took away that A and I took away that B, I'm still left with this one over here. And so there's my answer, right? And again, I think that's probably a good way to teach junior high kids because you can kind of visually see what's happening, okay? Okay. All right. So for the next problem I have here, y'all, we're just looking at to see which property is illustrated in each of the following. What I mean, which property, guys, are we using like the distributive property? Are we using the multiplication of 0? Are we using, let's see, the commutative property, which says you can reverse the numbers? Are we using the associative property, which means you can group them differently? Or are we using the identity property, which says we're multiplying something in here by 1? Okay, so let's take a look and let's see if we can't figure out how to do the next problem that I have here. Okay, so when I look at the first problem right here, y'all, the first thing I notice is the order of my numbers is still the same. It's 5, 4, and 3. It's 5, 4, and 3. But we grouped the 4, 3 here, and we grouped the 5, 4 there. The one that tells you when you group them differently is going to be the associative property, okay? When I look at the second part, and I want you to notice what's different. First, it was 4 times 3. Now it's 3 times 4. That right there, y'all, is the commutative property, okay? Now, I want you to notice this one here. The 4 and the 3 are grouped. Hey, the 4 and the 3 are still grouped. It is we switch the order. Again, that's still commutative property, okay? Okay, now part D says 1 times 4 plus 3 equals 4 times 3. That's the identity property, okay? Because we're multiplying by 1, okay? And in part E, I'm going to kind of write it over here because I'm running out. That's my 0 property, right? Because we know that when we multiply by 0, we get 0. And for part F, notice what we're doing. We're taking this guy times that, and then this guy times that. That's my distributive property. Okay, so just again, going through the process so I know which properties mean what. Okay. All righty. So, y'all, for the next problem that I have here, again, it just says, show that a plus b squared is equal to a squared plus 2ab using the distributive property of multiplication over addition and other properties. Okay, so I want to kind of walk you through the process so that we understand how do I know which one is going to be the correct answer, okay? So, y'all, I want you to notice here that it says a plus b all squared is supposed to be a squared plus 2ab plus b squared. Now, look at the final answers. The final answers are all the same. So that's not really going to help me, okay? What's going to help me is which is the one that looks like the work is correct. Okay, so when I have a plus b squared, remember, that really means a plus b times another a plus b, okay? I'm going to do this work on the side. And y'all, what I'm going to do here is I'm going to use my FOIL method. So remember, the first terms, a times a squared, okay? The outer terms, a times b, ab, okay? The inner terms, b times a, guys, ba is the same thing as ab. So if you want to write it ab or ba, that's still fine. And then the last terms, b times b is going to give me b squared. So now I have a squared. AB and BA really are the same thing. So if I have two of the same thing, I can write it like this and B squared. So what I'm going to do is I'm going to look at what I have right here, okay? And I want to see, okay, which one of those looks like they did the right thing. So guys, if I were to start working from this way to the end, well, look, they wrote it out correctly. That looks good so far. But notice from here, they took off the parentheses, right? But guys, if I were just to distribute that b times a would be a ba, b times b would be squared. How did I get that part? They didn't leave the a in parentheses. So I would say that doesn't look like it's correct, okay? Same thing right here. Look, here they distributed that part correctly, but where would the a squared come in from? Yeah, that doesn't look like it's right, okay? Did we multiply anything by 2? No, that doesn't look like it's right. Hey, here we go. This is what we had. okay? So my choice here would be A, okay? Okay, now there's a second part to that question, and it says, hey, show that A plus B all squared is equal to A squared plus 2AB using an area model. Okay, so let me explain what we're gonna do here, guys. I'm gonna do this over on the side again, okay? I should have put more space, I'm sorry about that, y'all. Okay, so what we're gonna do, you guys, is we're gonna make like a square here, okay? I'm gonna call this A, I'm gonna call this B, I'm gonna call this A, and I'm gonna call this B. Okay, what that means, you guys, is I'm gonna end up with something that looks like this, okay? Now, I want you to think about, remember, if I'm calling that A and that B, wouldn't the whole piece here really be A plus B, right? And if I'm calling this A and that B, wouldn't this whole piece here really be A plus B? Okay, because I'm adding them together. Now, remember how again, we didn't really talk about this in this class, but again, this is probably stuff that everybody here knows. Remember how you find the area of a rectangle? You multiply the length times the width. So A times A, that's going to give me an A squared, right? Okay, and A times B, well, that's going to give me an AB, okay? And y'all, if this piece is A, that means that that piece is A, that means that that piece is also A. So A times B, that should be another AB. And if this piece is B, that means that that piece is B, and that means that that piece is B. And if this is B, that's got to be B. So a B times B, that's going to give me a B squared, okay? And what I want to do now is I want to look at what I have right here, and I want to come back and see which one of those options that we have there looks closest to what it is we have, okay? So look, I got an A squared here, I got an AB right here, I've got a B squared right there, I got a BA right there. Okay, so so far that's looking pretty good. But I also want you to notice, look, I have an A here and an A here, and I have an A here and a B here. Hey, look, I got a B and an A. That doesn't look like it matches up, okay? Which one looks like it matches up the best? Probably C, right? C looks like it matches up the best. There's my A and my B and my A and my B, and everything else seems to be pretty good. The problem here, look, they got A and A. We know we didn't have that. They got B and B. I know that's not good. Again, they have B and B here and A there. Yeah, that's not good either, okay? Okay, let's take a look at the next problem that I got here. And it says, discuss possible error patterns in the following computation. Okay, so let's take a look-see here, y'all. I got 25 and 36. Okay, they're saying the answer is 90. Let's see if we know if that really is the case. So look, 6 times 5 is what, 30? And 6 times 2 is 12 plus 3 more, 15? Okay, guys, when we did this other day, we did kind of our partial sums, didn't we then say 3 times 5 is 15? Carry my 1 right here. 3 times 2 is 6, and 1 more is 7. Okay, so if I were to add straight down, that's 0, 5 and 5 is 10, and that should give me 900, right? So I should be coming up with 900. They have 90, okay? Let's see. It says the multiplication, so let's see what's the correct answer. Let's see. It says the multiplication by the tens in 36 was recorded in the wrong place. So the tens, was it recorded in the wrong place? 3 times 2 is 6. That should have been a 7, possibly. Maybe that's the one. Okay, it says the ones and the tens were multiplied separately and the products were added together. So guys, if they were saying the ones and the tens were multiplied separately and the products were added together, 6 times 5, that would give me 30. Those are the ones. The tens, 3 times 2 would give me 6. And if I were to add them together, wouldn't that give me the 90? So that looks like probably the best choice. And the last one says there are no errors, the multiplication is correct. Hey, I know that's not it, right? The necessary regrouping was not done. Yeah, guys, I would probably, I mean, it looks like A, B, and C all kind of seem to be fairly good answers. I would probably go with B and say the ones and tens were multiplied separately and the products were added together, because I do get that, right? I also agree that, you know, the multiplication wasn't done correctly, but I would probably go with B, the ones and the tens were multiplied separately and the products were added together. Okay. Okay. So again, y'all, we're going to go through figuring out reasons for each of the following steps, okay? So I want you to notice what they have. They have 45 times 10, and then they kind of break it down into a ton of different steps. So let's see if we can figure out what are we doing here, okay? So when I look at the first step, y'all, it says 45 times 10 equals 4 times 10 plus 5. Remember, 4 times 10. Why is it 4 times 10? Because that's how many tens we have. In 45, there's 4 tens and there's 5 ones. That right there, y'all, that's what we call our place value, right? So when we learned place values, like when we were back in school, 45 means that there's 4 tens and 5 ones. So that's what that part is really telling me right there. Okay, now I'm going to look at the second part. It says, the second step, 4 times 10 times 10 plus 5 times 10. Okay, so I want to see what did we kind of do here. I want you to look at, say, this line going into this line. Since this piece here is being multiplied, if I multiplied it by that, and I multiplied it by that, I would get 4 times 10, which I have right here, times this 10, plus 5 times 10. Y'all, that's my distributive property. We're multiplying that 10 throughout everything inside my parentheses here, okay? Okay, now my next step, I'm going to go from this piece here to this piece here. So I'm trying to see, what did they do? Look, they took the parentheses from the 4 and the 10 and they grouped them around the 10 and the 10. That's going to be my associative property. The associative property says you can regroup your numbers. You can multiply these over here first, okay? Now, I'm going to go from this step here to this step here. Notice what they did. They said 10 times 10 is the same thing as 10 squared. Hey, that's what we call raising a number to a power, right? If I have 10 times 10, I'm multiplying the number 10 twice, okay? All right, let's take a look here. When I look from this line here, you guys, to this line here, let me see, what did they do here? I still have the 4 times 10 squared. I still have the 5 times 10. Look what they added in. They added in the 0 times 1 business, right? So the 0 times 1 business, isn't that my identity property and my 0 multiplication property? Because that's really the only thing that changed there. Okay. And finally, 45 times 10 is 450. That is just my place value again, right? 45 tens, 450, that's just my place value again. Okay, so I'm just kind of going through the process, understanding which one of those properties are doing what. Okay, so y'all, let's take a look at this next problem here. It says, fill in the missing numbers, okay? So remember, we talked about partial sums the other day, and that's in essence what we're using here, you guys, okay? So look, we have 400 something 6 times 784 is going to give us this answer here. So let's think about that process of partial sums. Okay, so let's think about this for a minute. Look, y'all, when we multiply, 4 times 6 is going to give me what? 24? Okay, now I want you to notice the next part. We're going to take 4 times something right here, 4 times some number. So 4 times some number, and we're going to add 2 to it. When we add 2 to it, what should we get in our ones position? We should get a 0, right? Okay, so we should get a 0. Okay, so look, y'all, we're going to go like this. 4 times 1 plus 2. What is that? What's 4 times 1? 4. Plus 2 more? Okay, so I know 1 is probably not a good choice. Let's try like this. What about 4 times 2? What's 4 times 2? Plus 2 more? Hey, isn't that what that looks like that's going to work? Okay, y'all, so look, what we're going to do right here, I'm I kind of clean this up. Where's my eraser? Okay, so right here, I'm going to put a 2 because I know when I go 4 times 2, that's 8, plus 2 more, that's going to give me 10. Look, 4 times 4 is what, 16? 16 plus 1 more? Okay, and let me zoom out so we can see. So look right here, you guys. I'm putting a 2 right here, and look, there's my 7. Okay. Now, let's continue doing that same process, and let's see if this is really going to work out. Okay. So I'm trying to zoom out a little bit just so that I have some space here. And I'm going to clear those guys out because I've already used them in my carrying. I don't need to use them anymore. Okay, let's try again. 8 times 6 is 48. What's 8 times 2? 16. What's 16 plus 4? 20. Good. So I'm going to put my 0 there. I'm going to put my 2. 8 times 4 is 32. What's 32 plus another 2? 34. Okay. Hey, does that look like if I were to put a 0 right here? It looks like we're still doing okay, doesn't it? Okay, now, guys, I'm going to do this a third time. I'm going to clear those guys out because I've already done my carrying. Now, let's multiply by our 7. So 7 times 6 is 42. Carry my 4. 7 times 2 is 14, and another 4? Isn't that 18? Very good. 7 times 4 is 28, plus 1 more? 29, right? Okay, so look, guys, I'm going to put a 2 right here. Okay, and now all I'm going to do is I'm going to just add straight down, right? We're going to Adam and Eve here. So let's see, there's a 4, there's an 8, 7 and 2 is a 9, 1 and 4 is 5, 5 and 8 is 13, okay? 1, 3, and 9 should also be 13 and carry my 1. And so I end up with 333,984. So right here, I'm going to put my 8. And all I was trying to do, the biggest part here, y'all, was figuring out what number that I have to multiply there. And the way we did it, we said, look, 4 times 6, just to recap so everybody understands, right? The first thing we said is, look, 4 times 6 is 24. Carry the 2. And then since we didn't know what number was going to go right there, we said, look, well, let's try 4 times 1. 4 times 1 is 4, plus 2, that ends in a 6. And we didn't have a 6. So we tried 2. 4 times 2 is 8, plus 2 more, that's a 10. That ends in a 0. So we knew that that had to be a 2 right there. And that's how I was kind of playing that game. Does that make sense? Yeah? Good. Okay. So y'all, we just have a couple more problems to do here. Yeah, just 2 more problems. I think this, to me, this was probably like the most difficult problem, and I hope as we did it, it didn't seem too rough. But this next problem here says a car trip took 6 hours at an average speed of 52 miles an hour. The directions are telling me mentally compute the total number of miles traveled, or total number of miles traveled. Okay, so it's asking me to do this like mentally. Some people are great at mental math. Some people aren't. I want to show you the process because, you know, even though I'm going to do this mentally, I'm still going to write a couple of things down. I want you to think about the number 52 as 50 plus 2. Okay. Now, what's 6 times 5? 30. So 6 times 50, wouldn't that really be 300? Okay. What's 6 times 2? 12, isn't it? Okay. So now if I have 300 plus 12, isn't that 312? That's sort of the idea on how you would do it mentally. You would say 52, think about it as 50 and 2 separately. And so 6 times 50 is 300, because I know 6 times 5 is 30, and 6 times 2 is 12, and 300 plus 12 is 312. That's kind of the idea behind showing mental math. Y'all, for the next one that I have here, it's telling me to estimate the number of theaters in the seats, or the number of seats in the theater, I'm sorry. So it says a theater has 10 or 13 rows with 26 seats in each row. Estimate the number of seats in the theater. So remember, an estimate is a guess, but it's supposed to be kind of a good guess. So the way we're going to go through this process, y'all, in terms of estimating, let's round each of those numbers to the nearest 10. So if I'm going to round 13 to the nearest 10, my question to you, is it closer to 20 or is it closer to 10? Yeah, it's closer to 10, right? Okay, we're going to do the same thing for 26. Is 26 closer to 30 or closer to 20? 30. And if we multiply those numbers together, wouldn't that give me 300? And that's the idea. Behind the estimate, you're really just rounding to the nearest 10. If it had more seats, maybe you'd round it to the nearest 100, but you're kind of rounding to the next place value, okay? All right, so guys, that right there is 3.4. Now, I'm going to do something real quick before you guys leave. I want to show you guys something. Okay, so nobody else is here. Let me